Welcome, science fans! Imagine the universe as a giant Lego set. Atoms are the building blocks. But how do these blocks stick together to form everything we see around us? The answer lies in the captivating world of chemical bonding. Chemical bonding is the force that holds atoms together. It's the glue that binds them into molecules and compounds. Without it, our universe would be a chaotic soup of individual atoms. No water, no air, no you, no me. These bonds are formed by the interactions of electrons, those tiny particles that whiz around the atom's nucleus. Think of them as the social butterflies of the atomic world, constantly seeking to connect and form stable relationships. Understanding chemical bonding unlocks the secrets of matter. It helps us understand why water is a liquid at room temperature, why diamonds are so hard, and how our bodies function. Imagine two dancers, each with an outstretched arm. When their hands meet and clasp, they form a bond, moving together in harmony. Valence bond theory uses a similar analogy to explain how atoms bond by sharing electrons. Valence electrons are the outermost electrons of an atom, the ones involved in this intricate dance of bonding. Each atom strives to achieve a stable electron configuration, often by having 8 valence electrons, like a dance card filled with partners. Electron dot structures, also known as Lewis structures, help us visualize this dance. Imagine each dot as a valence electron. When atoms share electrons to fill their outer shells, they form covalent bonds, represented by lines connecting the atoms, where the dots represent lone pairs. This sharing of electrons creates a stable molecule, much like the balanced harmony of two dancers moving as one. Molecular orbital theory takes a different approach to understanding chemical bonding. Instead of electrons being confined to specific atoms, imagine them spreading out over the entire molecule, like clouds shifting and merging in the sky. These electron clouds are called molecular orbitals. They represent the probability of finding an electron in a particular region of the molecule. Some molecular orbitals are bonding orbitals, bringing atoms closer, while others are anti-bonding orbitals, pushing them apart. Think of it like two waves meeting. If they crest at the same time, they reinforce each other, bonding. If they clash, they cancel each other out, anti-bonding. This theory helps us understand the properties of molecules, such as their shape, magnetism, and how they interact with light. It's a more complex but comprehensive view of the intricate world of chemical bonding. To truly understand chemical bonding, we need to decode the language of atoms. 3 key terms help us do this: valence electrons, oxidation numbers, and electronegativity. Valence electrons are like the social butterflies of the atom, determining its ability to form bonds. The more valence electrons an atom has, the more bonds it can form. Oxidation number is like an atom's charge if all the bonds were ionic, giving us an idea of how many electrons an atom gains or loses during bonding. Electronegativity is an atom's ability to attract electrons in a chemical bond. Imagine it as a tug-of-war between atoms, with the more electronegative atom pulling electrons closer. These terms may seem like jargon, but they are essential for understanding the nuances of chemical bonding and predicting how atoms will interact. Ionic versus covalent bonds, a tale of two attractions. Chemical bonds are all about attraction, but not all attractions are created equal. 2 main types of bonds exist: ionic and covalent. Imagine a basketball player and a fan. The fan is drawn to the player's talent and cheers them on, much like a covalent bond. Now imagine the player giving the fan an autograph. This exchange creates a stronger bond of ownership and gratitude, similar to an ionic bond. In covalent bonds, atoms share electrons, like the shared admiration between the fan and the player. This sharing creates a stable molecule, like a team working together. In ionic bonds, one atom donates an electron to another, like the player giving an autograph. This creates ions, atoms with a charge which are then attracted to each other, forming a strong bond. Understanding the differences between these bonds helps us predict the properties of compounds. Ionic compounds like salt tend to be solids at room temperature and dissolve in water, while covalent compounds, like water itself, can be liquids, gases, or solids. Beyond simple bonds resonance, hybrids, sigma, and pi bonds. As we delve deeper into the world of chemical bonding, we encounter concepts like resonance hybrids, sigma bonds, and pi bonds, which add complexity and nuance to our understanding. Imagine a chameleon changing colors. It's not that it has multiple colors, but rather its true color is a blend of all of them. Similarly, some molecules are best represented not by a single structure, but by a hybrid of multiple structures called resonance structures. Sigma bonds are like the strong, stable foundation of a house. They are formed by the direct overlap of atomic orbitals along the axis connecting two atomic nuclei. Pi bonds, on the other hand, are like the decorations that add character to the house. They are formed by the sideways overlap of atomic orbitals above and below the bond axis. These concepts help us understand the stability, reactivity, and three-dimensional shapes of molecules, revealing the intricate beauty of chemical architecture. The octet rule: atoms seeking stability. Atoms, like people, crave stability. In the world of chemistry, this stability often comes from having 8 valence electrons, a concept known as the octet rule. Imagine an atom with 8 empty chairs around it. Each chair represents a space for a valence electron. Atoms will gain, lose, or share electrons to fill these chairs, achieving a stable electron configuration like a noble gas. This rule explains why noble gases with their already full valence shells are so unreactive. They are content with their electron configuration and have little desire to form bonds. The octet rule is a fundamental principle in chemistry, helping us understand the driving force behind chemical reactions and the formation of molecules. Exceptions to the rule: hypervalent atoms and hybridization. While the octet rule is a useful guideline, the world of chemistry is full of exceptions and surprises. Hypervalent atoms and hybridization are 2 examples that challenge our understanding of chemical bonding. Hypervalent atoms, like a party host who somehow manages to squeeze more guests than chairs into their living room, can accommodate more than 8 electrons in their valence shell. This is possible because they can access empty d orbitals, creating space for more electron pairs. Hybridization is like a chef combining different ingredients to create a new flavor. In chemistry, it involves the mixing of atomic orbitals to form new hybrid orbitals, which influence the molecule's shape and bonding properties. These exceptions remind us that the world of atoms and molecules is complex and ever-evolving, with new discoveries constantly refining our understanding of chemical bonding. From atoms to molecules, the significance of chemical bonding. Chemical bonding is the bridge between the microscopic world of atoms and the macroscopic world we experience. It's the invisible force that shapes our reality, dictating the properties of matter and the course of chemical reactions. Everything is made up of atoms held together by chemical bonds. These bonds determine the strength of materials, the conductivity of metals, the taste of food, and the colors we see. Understanding chemical bonding allows us to design new materials with specific properties, develop life-saving drugs, and address global challenges like climate change and energy production. The future of chemistry. Exploring the world of bonds. The journey into the world of chemical bonding is far from over. As scientists delve deeper into the quantum realm, they are uncovering new types of bonds and challenging our existing understanding. Researchers are exploring exotic bonds in extreme environments like the cores of stars and the depths of oceans. They are using advanced techniques to manipulate single atoms and molecules, paving the way for nanotechnology and molecular machines. The future of chemistry holds immense potential for breakthroughs in medicine, materials, science, and energy production, all driven by a deeper understanding of the fundamental forces that bind atoms together. Conclusion: the never-ending quest to understand chemical bonding. The quest to understand chemical bonding is a journey into the heart of matter, a journey that reveals the elegant simplicity and astonishing complexity of the universe we inhabit. From the basic principles of electron sharing and attraction to the intricate dance of molecular orbitals and hybridization, each discovery brings us closer to comprehending the fundamental forces that govern the interactions of atoms and molecules. As we continue to explore the world of bonds, we unlock new possibilities for scientific advancement and technological innovation, shaping the future of our understanding of the universe and our place within it. Be sure to have a nice night, and good night.